Hello and welcome to lecture 36. In last lecture, we were solving the numerical for 2-spool gear turbofan engine, in which the informations given are bypass ratio, that is 12.5, fan pressure ratio 1.5, LP pressure ratio 2.5, HP pressure ratio it is 12.8. Engine mass flow rate it is given, that is total mass flow rate 180 kg per second. Gearbox efficiency is 99%. Say gear ratio is 3:1 or we can say 1:3. It depends like what we are configuring. Then we are having say combustion chamber efficiency, it is 96%. Total pressure loss is 3% in combustion chamber and 2% in tailpipe. We have our turbine entry temperature to be 1800 Kelvin. And different component efficiencies like for intake efficiency is 90%, fan efficiency is 90%, for compressor efficiency is 86%, for turbine the efficiency is 92%, and for nozzles efficiency they are say 96%. So, we have solved the cycle parameters. So, here this is representing our TS diagram for the given information. We have calculated all station total pressure and total temperature at station 2, 3, 4, 5, 6, 7, 8, 9 and 10. We are interested in static property at the exit of the nozzle for the turbine nozzle. Same way at the exit of the fan nozzle we have calculated our static properties like pressure and temperature. Then we have done our calculation for the exit velocity. Now, let us move forward. So, here what we have it is say performance parameter calculation. We are interested in calculating the thrust, and that thrust we are writing in terms of cold thrust as well as hot thrust. So, for cold thrust we know it is given by m dot fan into V11 minus V infinity. This V11 it is exit velocity from the fan nozzle plus A11, this A11 it is area of the fan nozzle, P11 is a static pressure at the exit of the fan nozzle, P infinity is atmospheric pressure. Same way here this is representing my hot thrust, it is m dot core into bracket 1 plus F V10, this V10 is the exit velocity from the turbine nozzle, V infinity is our flight velocity. Similarly, A9 it is exit area from our nozzle, say turbine nozzle, P9 minus P infinity. So, we have all the information available with us. So, let us put all those numbers since we are considering this as a flight condition. So, we have V infinity as 241.93 meter per second, say fuel air ratio is 0.03. If we will be putting all these numbers, be careful this pressure what we are putting that need to be put in pascals. So, if we are putting all numbers, it says the net thrust is coming 22.09 kilonewton. Remember this number what all we are getting, that is for the flight condition. Okay. And when we are flying at particular altitude at the cruise speed or we say cruise condition, there our thrust requirement that is what will be lower. We want higher thrust when we are taking off, or we can say when we are having the ground condition. So, do not get confused with this number. Now, we have next parameter, it is thrust specific fuel consumption, it is m dot F divided by thrust. This m dot F we are calculating in terms of fuel air ratio into m dot core. We have this m dot core as 13.33 and thrust we have calculated. If we are putting this number, it says my thrust specific fuel consumption is 18.1 gram per kilonewton second. Be careful about the unit. Okay. Once we are having our thrust and thrust specific fuel consumption, our next target parameter they are say velocity say efficiency components. So, we are interested in propulsive efficiency, we are interested in thermal efficiency, we are interested in overall efficiency. So, let us do the calculation for that. If we are considering our propulsive efficiency, we know propulsive efficiency it is given by V infinity into torque, net torque Here this torque we are representing in terms of hot thrust and cold thrust. Okay. Same way here this is representing our kinetic energy term, and that together if we put all these known numbers, it says propulsive efficiency is coming to be 84.29%. We know for high bypass ratio engine, say here in this case what bypass ratio we are considering, it is high bypass, and that is the reason why this propulsive efficiency will be coming in these terms. Okay. Now, let us calculate the thermal efficiency. We know what is the denominator for the propulsive efficiency will be numerator here, and what will be our input energy we are writing in terms of mf into calorific value of the fuel. And if we will put these numbers, then we will be getting our thermal efficiency as 35.23%. Now, as we have discussed, people they are more interested in say thermopropulsive efficiency or overall efficiency, because propulsive efficiency for this kind of engine that is coming very high. So, if you are comparing your engine, turbojet engine, turbofan engine, the same may be turbosaft engine or say turboprop engine, all these together it is not making sense in terms of comparison, and that is the reason why people they are putting this term as say overall efficiency. So, let us put these numbers. If we are putting this number, the overall efficiency is coming to be 29.70%. So, let us put this all together. It says when we are having our flight velocity condition, for that flight condition we have temperature and pressure. Based on that we have done our calculation for the exit area from the turbine nozzle as well as fan nozzle. We have done our calculation for the net thrust, thrust specific fuel consumption, propulsive efficiency, thermal efficiency and overall efficiency. Now, this will be the information for what all numbers we have selected with. We are more interested in understanding what will be the effect of change of our cycle parameters on the performance. So, let us discuss about that. What is our interest here? Say performance parameter for our turbofan engine we are defining as a thrust or say maybe specific thrust, thrust specific fuel consumption, fuel air ratio, propulsive efficiency, thermal efficiency and overall efficiency. Now, these are the main basic parameters, and that is what is always been the interest for our say gas turbine engines. Let it be any kind of engine. Okay, for all of them we are configuring this as our performance parameters. So, we know these performance parameters they are being affected by say compressor pressure ratio, we can say overall pressure ratio, which includes say fan pressure ratio, LP compressor pressure ratio, HP compressor pressure ratio, what is our bypass ratio, what will be our turbine entry temperature, say efficiency of different components, say diffuser, fan, compressor, combustion chamber, turbine, nozzle, they also have impact on the performance. So, what all cycles till now we have say done the calculation where we have discussed the performance parameters, we have not discussed about this efficiency term, because it will make its own sense, and this what we are discussing about the components basically that is been verified computationally as well as experimentally, and then after they are considering the best efficiency numbers. And in week 2 we have discussed what could be the initial assumption in terms of efficiency of all these components. So, again if you want you can revise what we mean by the component efficiencies. Then here we are discussing about the flight condition, it may be ground condition. So, when we are flying at particular altitude at particular speed, that also has impact. So, we will be discussing this all parameters on the performance of the engine. So, let us look at very first parameter. We say we have our fan pressure ratio and we will be putting other parameters to be constant. Let me put the point here, what all cycle analysis we are doing, we are putting one parameter as a variable parameter and what will be the impact of this parameter on different performance parameter. But you can make composite curve also. If What we mean by composite curve is maybe you will be having 3 parameters which are varying, and you will be having 2 or 3 parameters, that is what will be showing the impact of change of parameters. It will be making the confusion, and in order to avoid such kind of confusion, we are taking single parameter. This all together you can put in one plot, that is what is called carpet plot. That also is possible, maybe as and when required. In later case, I will show you what exactly we mean by this carpet plot. Okay. So, let us look at the first parameter, it is say fan pressure ratio. So, here in this case, this is representing our variation of fan pressure ratio versus thrust. So, if we look at when we are increasing our fan pressure ratio, we have cold thrust, that is what is going to be increased with the increase of fan pressure ratio. The reason we can clearly understand the meaning, what velocity we will be having from exit from our cold nozzle, that is what will be higher. At the same time, say amount of power required by my LP turbine in order to run fan for this particular pressure ratio will be higher, and that is what will lead to reduce the exhaust enthalpy. We can say this exhaust enthalpy, that is correlated with the exhaust velocity, and that is how we will be having our hot thrust, that is what will be decreasing with the increase of fan pressure ratio. In overall, we can say rise of thrust because of say cold stream it is higher, that is what will be result in so overall thrust, that is what will be increasing with the increase of fan pressure ratio. Okay. Now, if we have this rise of pressure that will give the rise of thrust, we can say our specific thrust that also will be increasing with the increase of fan pressure ratio. Okay. Now, let us look at the next scenario. Here in this case, we are interested in thrust specific fuel consumption. We can say, since my thrust it is coming in the denominator, so it says with the increase of fan pressure ratio, we will be having decrease in thrust specific fuel consumption. Again, you will be having the variation in mass flow rate of the fuel, but that variation is small compared to the variation of the thrust, and that is the reason why we are having our thrust specific fuel consumption to be reduced. Okay. Now, let us look at what is happening with our efficiency term. So, here since we are discussing about the flying condition, so we will be having presence of all the 3 efficiencies, say propulsive efficiency, thermal efficiency and overall efficiency. So, here in this case we can say with increase of fan pressure ratio, we will be having rise of say thermal efficiency. You can see here in this case we will be having say rise of my cold thrust, that is what will be lead to increase our thermal efficiency. So, this thermal efficiency is going higher, at the same because my cold thrust is higher, that is what will lead to increase our propulsive efficiency, and in overall sense we will be having say rise of overall efficiency with the increase of fan pressure ratio. Okay. Now, this is what is representing the effect of fan pressure ratio. Let us consider say we have our next component, that is what is say LP compressor. So, let us discuss about what is the effect of LP compressor pressure ratio. Suppose if I consider say LP compressor pressure ratio, we know our LP compressor and fan, that is what will be rotated by our LP turbine. So, here in this case we can say when we are increasing our LP compressor pressure ratio, it has no effect on cold thrust because it has nothing to do with the exhaust of our fan, but with increase of LP compressor pressure ratio, our hot thrust will be going to be reduced. So, here again we can say what we mean by increase of pressure ratio, that is what will be demanding for increase of our power from the LP turbine, and that is what will lead to reduce the enthalpy at the entry of the nozzle, and that is what will lead to give say lower velocity, and that is what is coming here in terms of reduction of hot thrust. So, in overall if we look at with the increase of LP pressure ratio, we will be having reduction in thrust. When I say there is a reduction in thrust, that is what straightway will reflect in terms of our specific thrust. So, it says with the increase of LP compressor pressure ratio, our specific thrust, that is what will be reducing. Now, any guess what will be happening with our say thrust specific fuel consumption, since that is also the function of my thrust. So, here in this case, if we will put my thrust specific fuel consumption, it says when we are increasing our LPC pressure ratio, we will be having reduction in thrust specific fuel consumption. Okay. Now, let us look at what will be the impact on the efficiency term. So, here in this case we can clearly see with the increase of LPC pressure ratio, our thermal efficiency, that is what will be increasing. We will be having the rise of propulsive efficiency, and in overall sense we will be having rise of say overall efficiency with increase of LPC pressure ratio. Okay. Now, on say left hand side, this all are representing the equations. So, you need to understand what all will be the impact of change of LPC pressure ratio on these parameters, these highlighted parameters. Mainly they are impacting on our velocity, exit velocity. Second impact, that is what will be on say hot thrust. Third impact, that is what will be with the exit velocity, and V10 we know that is what is exit velocity from our turbine nozzle. So, they will be having direct impact on these parameters. Okay. So, this LPC pressure ratio, it says we will be having reduction in the thrust. Let us look at if we are increasing say HPC pressure ratio, what all will be the changes. Say for HPC pressure ratio, we know it has no impact on our cold thrust, but similarly we will be having the impact on the hot thrust. So, this is representing our design condition. With the increase of HPC pressure ratio, we will be having reduction in thrust. This reduction in thrust is not with a great number, be careful about. Okay. And here if we look at, it says that is what will lead to reduce our specific thrust. So, carefully observe what all are the numbers on our y axis. Okay. When we say with increase of HPC pressure ratio, we will be having reduction in specific thrust, but by what number, that is very important. So, this is representing our design condition. That is the reason why for all the plots we are putting say our design condition. Okay. Now, let us look at the variation of this HPC pressure ratio. Here this is our design condition. So, it says when we are having our HPC pressure ratio to be lower, we will be having our thrust specific fuel consumption to be higher. With the increase of this HPC pressure ratio, we will be having thrust specific fuel consumption, that is what will be reducing. So, this is giving the indication what should be the number and from where we are configuring these numbers. Okay. So, here also if you look at carefully, say for the variation of HPC pressure ratio in this range, if you observe carefully, not much variation in terms of thrust, that is what is happening. Okay. So, let us look at what is happening with the efficiency. So, if we try to observe the efficiency variation, so it says for the lower pressure ratio, lower HPC pressure ratio, my thermal efficiency will be lower. With the increase of HPC pressure ratio, we will be having the rise of efficiency by almost say 4 points. Okay. That is what is a big number. Okay. Now, here if you look at, this is representing the increase of propulsive efficiency with the increase of HPC pressure ratio, and in overall if we observe, this is representing the improvement of overall efficiency with the increase of HPC pressure ratio. Now, we can say we have indication, maybe if we are increasing our fan pressure ratio, say our LPC pressure ratio, HPC pressure ratio, they all lead to increase the efficiency in terms of thermal efficiency, propulsive efficiency. Same way we have small improvement in overall efficiency also. Let us look at the other parameters. Say maybe we will take the next parameter as a bypass ratio. Now, we know this bypass ratio that has impact straight on our cold thrust. So, let us look at what is happening. Okay. So, here it says with the increase of our bypass ratio, our cold thrust is going to be increased. Suppose say if I am selecting my bypass ratio to be lower, say maybe 6, then it says my hot thrust will be higher. With the increase of the bypass ratio, our hot thrust it is going to be decreased, and this decrease, that is what is reflecting in terms of my net thrust. So, with the increase of bypass ratio, it says my thrust, that is what is going to be reduced. Okay. Let us see what is the impact on the specific thrust. It says with increase of the bypass ratio, our specific thrust also is going to be decreased. So, here you can say this is representing our specific thrust at the design condition. Now, what will happen with our specific fuel consumption? So, what is our understanding? It says when we are increasing our bypass ratio, again and again we have discussed, with the increase of bypass ratio, our specific fuel consumption, that is what will be reducing, and that is the reason, if you recall, we are moving towards the adoption of gear turbofan engine, where we will be having larger size fan, that is what will be incorporated in order to achieve high bypass ratio. So, you can say this is representing our design condition. Let us look at what is happening with our efficiency term. So, here in this case, if we look at with the increase of the bypass ratio, up to certain extent we will be having a rise of thermal efficiency. Okay. And here if you look at beyond that point, we will be having the increase of propulsive efficiency. So, maybe it will be preferred, you can just check with the number of bypass ratio to be 18, and why is it happening? That will give you some new indication. That is what we will be discussing in our next lecture also. Okay. So, let us see here, this is representing the improvement of thermal efficiency with the increase of our bypass ratio. That is what will lead to improve the overall efficiency also. Okay. Now, once we have this as our impact, all this we are assuming these parameters are fan, compressor pressure ratio, turbine entry temperature, mass flow rate, all those parameters we are considering as a constant. So, let us look at what is happening in terms of the change of turbine entry temperature. So, we know when we are increasing our turbine entry temperature, that is what will lead to increase our hot thrust. So, it says if we are increasing our turbine entry temperature from say 1600 to say 2300, it says there is an increase of hot thrust. My cold thrust will not be having any impact of that. In overall, we will be having say rise of thrust with the increase of turbine entry temperature. So, let us look at this as a case. Here in this case, this is an indication of specific thrust. It says with increase of turbine entry temperature, our specific thrust, that is what will be going to be increased. Now, very important parameter as and when we are discussing is our thrust specific fuel consumption. Okay. So, this thrust specific fuel consumption what we have, we can say it is reflecting here with the increase of turbine entry temperature, we will be having the increase of thrust specific fuel consumption. Okay. So, if we are increasing this turbine entry temperature, that is what will lead to increase the amount of fuel consumed, because we want to achieve that higher temperature. Okay. So, let us look at this as a point, and here this is interesting observation. Say when we are increasing our turbine entry temperature, my thermal efficiency will be going to be decreased. Okay. So, when we are going with the higher temperature, we will be having reduction in propulsive efficiency as well as we will be having reduction in overall efficiency. Okay. Now, so sometimes we are thinking of increasing the turbine entry temperature, as we have discussed in the terms of our turbojet engine. That logic straightway is not applicable here. It has many impacts in terms of my velocity components, what we are calculating. It has impact on, say, my fuel consumption. Okay. Now, let us look at what is happening with my mass flow rate configuration. So, it says when we are increasing our total mass flow rate. So, it says it will be increasing my fan mass flow rate as well as my core mass flow rate, and that is what will lead to give the increase of, say, total thrust. Now, here in this case, with the increase of, say, my total mass flow rate, since this term here it is coming in terms of, say, thrust specific fuel consumption. So, it says with the increase of total mass flow rate, we will be having, say, reduction in thrust specific fuel consumption. And if we look at this, is representing what will be the change of area for these nozzles. So, when we are increasing our total mass flow rate, in order to handle that large mass flow rate, we need to have larger area of the nozzle. Okay. And if we look at, it has not much impact on in terms of, say, overall efficiency and thermal efficiency. Just be careful what it says, what number we are configuring. It says with the increase of total mass flow rate, we will be having, say, rise of thermal efficiency. My propulsive efficiency, that is what will be not varying much, and my overall efficiency also will be remains constant in that case. Okay. So, this is an indication of effect of change of mass flow rate. Okay. Now, let us look at what is happening with our flight Mach number. We are configuring all the parameters to be constant. It says when we are increasing our flight Mach number, up to certain extent we will be having my hot thrust, that is what will be, say, nearly constant, and later case my hot thrust will be reducing. At the same time, if we look at for the cold thrust, it says we will be having reduction in cold thrust with the increase of flight Mach number. Just realize one thing, what we mean by change of Mach number, that is what will be impact on my mass flow rate, that is what will be impact on my velocity, and that is the reason we will be having, say, reduction in, say, cold thrust, and later part it says we will be having the increase. In overall sense, we can say for this design condition of 0.82, we will be having with increase of flight Mach number, the thrust will be reducing. Okay. And this is representing our specific thrust, that also will be reducing with the flight Mach number. Just realize one thing, when we are increasing our flight Mach number, accordingly my pressure, temperature, density terminology, they all will be changing, and that is what has direct impact on specific thrust. Let us look at what is happening with the thrust specific fuel consumption. So, it says with the increase of flight Mach number, our thrust specific fuel consumption, that is what will lead to increase. Okay. And we have certain number, that is the reason why, if you recall, it says this commercial aircrafts, they are flying at, say, maximum Mach number in the range of 0.8 to 0.85. There is, you need to have some compromise in terms of performance if you are increasing your flight Mach number in terms of, say, consumption of large amount of fuel. Okay. And here this is representing the variation of thermal efficiency, propulsive efficiency, and overall efficiency. So, when we are moving at higher flight Mach number, we will be having higher propulsive efficiency, and that is what will lead to give the higher overall efficiency. Okay. So, this is what all we are discussing in terms of our, say, configuration of the engine, where it is flying at some flight Mach number of 0.82. Now, let us take the next numerical here. This numerical we will be taking, say, variant This variant we are considering here as bypass ratio. So, all other information that is what will be same here, rather changing other parameters. We want to observe what is happening with my performance parameters in terms of thrust, thrust specific fuel consumption, thermal efficiency, propulsive efficiency and overall efficiency. So, earlier case we are having bypass ratio of 12, here we will be configuring our bypass ratio to be 16. And in order to solve this numerical, you are matured enough. Let us try to solve this numerical with all information available with you. You know, like what all components we have, we will be putting those components. Based on that, we will be calculating our parameters at the exit in terms of pressure as well as temperature. We will be calculating our static temperature and static pressure at the exit of the nozzle. Based on that, we will try to calculate the velocity and we will try to calculate the performance parameter. This configuration, it is been taken purposefully. In next lecture, we will be discussing what all will be the impact of change of this bypass ratio, and we will be discussing the results in detail. Then we will be comparing that in terms of say open source literature. So, here we are stopping with. See you in the next lecture. Thank you.